Welcome back to our course on fundamentals of attosecond science and technology, brought from us at IIT Madras and IIT Tirupati. So, we are in the ninth lecture, but we have already crossed, I think we are in the 8th week of this course. So, the lecture numbers are slightly differently numbered. They are organized more by logical content. We are in the second module, which we hope to finish soon and move on to the next. So, as always, we begin with communicating about the reference texts which we used, which we have used in this, in preparing these lectures, and also acknowledging primary sources, particularly Professor Trebino for his inputs and materials, which he has generously shared not just with us, but with everybody online. The books we used, we have a new addition today. I have included the book by Diels and Rudolph, Ultra Short Laser Pulse Phenomena, in addition to the books by Roulier, Shank and the classic Born and Wolf. So, we will do a quick recap, and we just did it yesterday for this week. So, we do not probably need to dwell too much on it, but we will continue our discussion on chirp, characteristics, linear and quadratic chirp, higher order chirp, then have a quick peek at propagation of pulses and the idea of time bandwidth product and the consequence of chirp and other pulse characteristics on this important little metric, which will lead us on to metrology or measurements of pulses. So, let us jump into the recap as we speak. Today, I think we understand this iconic picture much better, which we have been flashing for now even a couple of weeks. Almost tends to get boring seeing this picture. But then today, this is this view graph of time versus electric field has a very pertinent meaning, because we just learned from scratch ab initio as to how pulses get this feature where the incident, I mean the electric field oscillating in the pulse essentially has a time varying frequency, right, which in this case increases in the increasing direction of time. And just yesterday we realized that this notion of instantaneous frequency, which we have developed now in this course, has a very good physical meaning, and in this case the increase in frequency, if I were to have, if I had plotted the instantaneous frequency say nu instant on the right, on the axis to the right, this could well have been something which increased from an initial, no, nu naught could well be somewhere at the center here. Nu naught, the central frequency of the carrier close to the, if you wish, the 0 of the time axis here, and the positive and the negative side. So, this is a characteristic linearly chirped pulse with a Gaussian envelope. All these pulses, not just the well behaved ones, but everything is indeed described by this now equation, which we have become friends with. E of t is the square root of I of t, the real amplitude, multiplied by a product of two complex exponential factors, one concerning the carrier frequency, the fast oscillations under the envelope, and the other being the temporal phase. And we half of this plus the complex conjugate is the real electric field as a function of time. We can write this down in the frequency domain by Fourier transforming it, and we get almost a one-to-one map. There is a temporal intensity and temporal phase, and there is a spectral intensity and spectral phase, and we can relate these quantities to the field itself, as we have seen how to do. And we can start with the simplest of pulses, where the envelope is a Gaussian, a function easy to Fourier transform and also close to what real world lasers produce, and the simplest case where the temporal phase is flat, consequently the spectral phase is also flat, which in our current level of discussion means that phi naught is not 0, but phi 1, 2, 3, all the higher order phi's are 0. Or it could even be 0 if you wish. This is constant. This could even be 0. The constant that it is could be 0, whereas necessarily the higher order coefficients in the Taylor expansion of these, well, the coefficients do not depend on time. So, this is in the time domain, whereas this is in the frequency domain. And the notion of instantaneous frequency gets built up from the fact that the we consider, if we start considering higher order non-linear and nonlinear terms in the Taylor expansions of phi, either in time or in space, we would essentially have a non-trivial instantaneous frequency, which is not necessarily just omega instant fixed to omega naught, but you have a derivative of the phi with respect to frequency. And group delay is essentially the converse of the factor d phi by dt we have in the instantaneous frequency, and here group delay is d phi by d omega. So, the Taylor series expansion of this is essentially the way to think about the phase factor phi of t, which is related to the instantaneous frequency. The instantaneous frequency is nu instantaneous. Function of time in its most general form is nu naught minus d phi by dt. Likewise, in the frequency domain, we have the spectral phase function, that is phi of omega. This again is expanded using a Taylor series, whose 0th order term, which we interpreted, which is identical for the space and time domain, to be the absolute phase, the initial phase. It is related to the carrier definition of the carrier envelope phase, which is relevant for few cycle ultra short pulses. And we also have the higher order terms with coefficients of Taylor expansion having particular interpretation. Phi 1, which is d phi by dt at omega naught, is the group delay. Phi 2, which is d phi 2 by d omega to the second derivative of the spectral phase function calculated at the central frequency omega naught, is a group delay dispersion. We saw what that means. The 0th order phase essentially is important for pulses close to a single or a couple of cycles underneath the full width at half max of the envelope. There the shape of the electric field can be determined in some sense or parameterized using phi naught. This can indeed even be measured, and in this case the iconic measurement of a trace of something that is on the time scales of the carrier for an optical pulse, which is a few femtoseconds long in its temporal duration, that is the full width at half max of the envelope is but a few femtoseconds, while while the optical cycle itself is a little over a couple of femtoseconds, is shown here, and the measurement of the carrier envelope phase using a phase meter is something which is possible. We will learn about this subsequently in this course. We can also consider the frequency variation or adapt an entirely frequency domain picture, where we said that any slow variation in phi naught, which is a constant, but if you have a very slow temporal variation in phi naught, this would of course imply that it is no more a constant, and therefore, in the Taylor sense this would not be rigorously the way we thought about it. But if we chose to, for example, deliberately modulate this quantity, right, when a train of pulses is being emitted by a laser, then the comb of frequencies that we measure for a pulse train, for a train of pulses, which we considered early on in this course when we discussed the Fabry-Perot interferometer, the comb would essentially have an offset away from 0 when the actual frequencies of the resonant modes is extrapolated down to 0 as shown here, and any temporal variations in phi naught, either systematic or not even that systematic, would essentially impact the offset of this comb away from 0. We then looked at the first order phase shift and first order phase term in the frequency domain interpretation of the phase function phi omega, the spectral phase, and realized that this essentially owing to the Fourier transform properties, that is the shift theorem. This is essentially just a shift in the time domain, which is the domain in which we are used to thinking about pulses. Now, in this lecture, we will reconnect with the previous session and look at the second order phase, where the pulse is said to be linearly chirped, that is the instantaneous frequency varies linearly in time, that is in time within the envelope of the pulse, and we essentially have here the center of the pulse envelope marking the 0 of time, because we choose a reference frame in which we are running along with the group velocity of the pulse, which is in some sense the average velocity of the constituent frequencies which make up this pulse in itself. And in this case, since the instantaneous frequency increases going from left to right on the time scale, from the negative to the positive side, this linear variation in frequency is called chirping, and this pulse is chirped. Had the pulse not been chirped, the carrier frequency would have been identical all over all through the pulse. The carrier frequency would have been identical at every instant of time, irrespective of where I measure this using a hypothetical detector within the pulse itself. Okay. Now, a linearly chirped Gaussian pulse as a consequence has not just the first order term in the phase in the argument to the exponential function. Yeah. So now the linearly chirped Gaussian pulse that we have been discussing essentially has in its argument to the complex exponential function two terms, one which is linear in t omega, which is omega naught t plus beta t square. Okay. So, we can take this sort of composite view of the exponent of I omega naught t plus beta t square, this the phase part of this function. We can essentially treat this the following way. We had viewed this earlier as omega naught t minus phi t. Okay. Phi is a sort of phi captured the slow variations in the phase, which are the variations of phi are slower than the time scale of 2 pi over omega naught. Okay. This is the cycle period, and these variations in the phase are slower, right. So, we saw this earlier too. So, this is the fast time scale, and d phi by dt is typically much smaller than anything to do with omega naught. This is slow. Okay. So, it is in this sense that we wrote this function, but I wanted to clarify a bit in the way we have written the mathematical expression for a Gaussian pulse. In that we have not considered the first order term of phi of t in writing this, which is the term, the phi 1 term does not seem to appear in the expression for the a linearly chirped Gaussian pulse. Okay. If you note that, I should have had an alpha omega naught t plus alpha t plus beta t square. Alpha t is actually redundant because it gets added or subsumed by omega naught. We have omega naught, we should ideally have had exponent of I omega naught t plus, we should have had a phi naught here, we should have then phi 1 of t plus phi 2 t square. All the other higher order terms are 0. So, it's the math is sort of trivial. Okay, let me get all my brackets right, but this is approximately omega naught because d phi by dt, any variation in d phi by dt we said is much slower than omega naught. That is one way to look at it, in which case we make a slight approximation, but one should really be careful in phase terms. Even small variations or deviations in phase numerically can still have substantial impact in these realizations. Think about interference. A more rigorous way to approach this would be to consider the electric field to be of the following type, right. Now, let me use a different phi for this. Exponent of I, capital phi of t. Capital phi is a total phase function. It has everything about the phase of the pulse that you want to know about, we care about. This has omega naught, this has everything. And then We can then talk about Taylor expanding this as a phi naught plus phi 1 of t plus phi 2 t square and so on and so forth. Here phi 1 is omega naught plus the alpha t which we should have had here, whereas phi 2, okay, there won't be a t here, it would then have omega naught plus alpha, omega naught and alpha going back to our previous definitions, but this entire thing constitutes the carrier frequency. And we only need to consider ourselves the the higher order terms that are present in the Taylor expansion. Okay, depending on the way in which we do these definitions, a factor of 2 may or may not appear. So, one should be careful in a rigorous exercise, one should track these things carefully along with the factors of 2 factorial, 3 factorial and so on arising out of in a Taylor expansion. But then the point I am making is that a typical Gaussian pulse, okay, at any instant of time, if I take a snapshot of its field amplitude, it essentially has a carrier component and then chirp, if any, is captured by the beta t square part. Okay. Now, we looked at this yesterday and in our discussions realized that the way in which we have defined the time axis while working in the co-moving frame where the observer, if you wish, moves along with the pulse's group velocity and therefore can have a steady view on the pulse itself. In that case, the beta or the chirp having a particular sign which is positive here on one side of the pulse, since t takes both negative 0 and positive values on either side of wherever we choose to mark the 0 of the pulse scale, which is typically set to the symmetry point on the envelope for something like a Gaussian pulse. Then on one side beta for t is equal to 0, the two terms tend to partially cancel out each other and the effective instantaneous frequency on one of these sides is lower than omega naught and on the other side it is higher than omega naught. The beta t, the omega naught term adds on to the value of beta t square, whereas it subtracts out from beta t square on the negative side. Okay. Therefore, this kind of instantaneous frequency variation in the pulse, the phase itself varies quadratically across the time axis, whereas the instantaneous frequency varies linearly.